everything. She used to wear glasses. Here she's cross-eyed. She was born with a misshaped head. She needed surgery. Facial surgery. It's pretty standard, not standard, but it's pretty successful. Procedure. Used to be a complicated thing because they think of back in like animal bones. There's like suture right here. And when you're an adult, if you invade their separate groups.
Bonjour.
One side, just one side.
About pretty.
Was growing this way.
Actually,
This had to be
what did you
cut.
answer?
I said hello.
I answered with great pleasure.
That's a big
In French?
scar.
Oh. You know a lot of...
Actually, this has to be taken too because it's already.
In a couple of words,
So it has to be. This has to be shaped too. So I think they took. There is like this frontal or circle,
Are we having a final project in this
but like
class?
everything like here.
If you want to.
I don't want
Now
to.
reshape.
Oh,
Again. I don't know.
Well,
It sounds scary, but
Why am I
it's so
asking?
like
Because
advanced.
if we do, I would like to start at
Oh,
back in the
because
60s and 50s,
like,
he used to
the
have
end of the semester is going to be very, very
few
crazy.
percent.
Well, that's what I'm saying, if we do it, should we not do at the end of the semester?
Well, I don't think you can ban that. I think they
I don't know.
like
Because I have I have
some of the
two
bone off.
reports due the first week in May. I have my minis the week before May.
If you grows like this, then
Like this
depending
week,
how it's
both of my classes.
and if this
exam
doesn't grow,
Thursday,
the
Friday.
bone is just like
there is a challenge in this class.
you got shape some.
The material is very diverse.
I'll
In
take that
this,
to jail science.
to design a project is not easy. In previous class, in both previous classes, it was super easy. Apply the same algorithm to different systems.
Yes.
So if you decide to go with project, it will impose more work for me.
Okay, so I say we.
I'm not
don't
telling,
impose.
I'm not telling no, but if I would like to go for it, it means I need to pay myself, like sitting and designing how to make this project.
Okay, sounds good.
Oh, yeah, I got bumped.
I got bumped to last. He might have just printed it as they came in.
No. The schedule.
What do you mean?
Oh no,
I was
we
second.
did get changed quite a lot. Because I was like third.
I was second. That's okay. Now you're last.
Right, we should be. First, the last will be first.
No,
Someone got a haircut.
the
It's the- do you see
I
this?
swapped on with two.
Do you see Sam's
Uh-oh.
Hey,
Get a haircut.
I did. Yeah.
haircut? That's why I said, did you see Sam's haircut?
I love that observation, like when people are, you got a haircut. Looks good, it's like because they never look like crap.
I would.
We ready to start?
Yeah, I will announce. So do not rush so rapidly.
Yeah.
Well,
Dan's presentation is gonna be quite informative.
It's noon. Let's go.
there is 1 minute before noon.
Well, you'll see when I get. It's not. It shouldn't be as informative as it. It looks.
It looks like I don't understand any of this.
Well, there are some ideas that you just need to like be exposed to and just like take by faith, not go
So
really deep into
postulate.
the mathematics.
Like a postulate.
Not a postulate. It's solid mathematics, but I just gotta tell you that it's there, just so you don't think that this is some kind of made up stuff.
Okay.
Because this is very complicated.
I think all of them are quite complicated, but I think yours might be the most complicated.
Well, it's because you gotta derive a theory that's like at the highest level of modern day computations.
Yeah, and that's why I laughed when you did your, I think, APS presentation last year, and Svetlana was like, you do not need to talk about GW. Everyone in the audience will know what GW is. I'm like, not a clue.
Yeah, that's
Do you remember that?
He's been gaining a lot of momentum lately.
George W.
I just want to explain what G and Tau is.
It's so unusual because typically all methods are named after the people. It is maybe one of the very few cases when it actually means something rather than abbreviating names.
Yes. Doesn't mean George Washington.
But actually the first can be considered as a name, like green, not as a color but as a person.
Yes, G comes from Green's function.
Today on
Do you think it is enough? Or some of you are tall enough? So
I think it'll be fine.
I think you're the tallest.
well, you don't want to make a record with headless speakers.
I might be wider than that.
Good arrangement? Well, if you will try to focus on the board, then everything will be corrupt and we will need to reset it. But if you stay here, should work. And you know, there is a... I never used it, but there is an opportunity to use this touch screen and make notes if you need some equations to be added. Just come there and write something. Okay, so who we are and what are we doing? It is a part of the a little bit advanced quantum class, CHEM767, and the general goal of what we do in the class is to solve unsolvable. So apply approximate methods, find approximate solutions of the problems that are a little bit more complicated than trivial problems in regular quantum course. We did cover the 3 chapters on angular momentum, time-independent perturbation theory, and time-dependent perturbation theory, with each chapter concluded by presentations of class attendees, giving more focus on applications. And I want to give credit to all of you in the sense that it is not only applications, it is triple thrust, triple impact that you are doing. You're looking broader to applications. Some of you are looking deeper into theories that we will have no chance to cover in the class. And some of you are looking forward in time to the theories that we may consider in class, but not right now, but later. So you are covering 3 directions. And the program, the presentation includes 6 speakers. Actually, it's everyone from the class. With the plan of these arrangements is to cover a little bit more of theoretical backgrounds and new theories for the first 2 and this. And then there will be 3 applications of theories that we already covered, to the application to the NMR spectroscopy, to optical spectroscopy by Mohammed and Sam. And there will be one talk that looks forward in time to the advanced spectroscopic techniques that we will try to consider in the next chapter. And same as previous time, Sam was telling about applications of time-dependent perturbation theory, although we didn't cover it in class. Today, Levi will talk about applications that needs additional theoretical methods. So we have about an hour, so let's try to stay within, well, if I say 3 minutes, it will be impractical, but like 6 minutes, maybe 7 minutes with questions per talk. We have some flexibility, we do not have the hard cut, but brevity is a sister of a talent. So if you're brief, it means it's good. If it is possible, do not just show, like, look on my slides, done. You need to explain something. So, practical arrangement. The slides are downloaded to this desktop, and you can see them right here. So first, second, third, fourth, fifth, sixth. So you come up, click on the number 1, and click if you do not like, if you do not use Microsoft in your everyday life, click here on the start presentation. With this, I would like to announce the first speaker, DEYAN MIKHAYLOV, who will tell us about connections between time-dependent perturbation theory that we studied in class and an important method in computational chemistry, so-called GW method. Floor is yours.
Okay.
And look so that you stay in the camera if possible.
Oh, okay.
See?
Yeah, okay. Is there some kind of pointer, laser pointer?
Use your finger. You're right next to the screen.
Oh. Okay, laser pointer doesn't work on the screen. Okay. Okay, so connection with GW and many-body perturbation theory is going to be made easier if someone kind of knows what the GW approximation is. Well, first of all, let me. This is tilted, but that's fine. It's supposed. This is supposed. Anyways, so as you can see, GW gives very good corrections to the band gap, predicted by local density approximation. So this should be exciting for computational chemists here. So, but when one goes to look up what GW is, Wikipedia gives you this answer, which is not very illuminating, and it's technically wrong the way they have worded it. So let's see what this GW all means. So first of all, I wanna kind of introduce creation and annihilation operators. That's how you do many-body quantum mechanics. So some of you have seen them, but you haven't worked with them, so you don't really know how they work. So let's say we have a harmonic oscillator with 4 particles in it, in the ground state. In many-body quantum mechanics, the ground state will be written like this: 2 particles, 0 in this state, and 0 in the 4th state. So this is kind of like a many-body state.
So you populate harmonic oscillator with fermions.
You populate harmonic oscillator with fermions, and let's say you know what the wave functions of these fermions are. In harmonic oscillator, you can calculate them exactly, or in complicated system, you can run DFT and say you can construct the densities, right? So annihilation operator doesn't have the dagger here. Creation operator has the dagger on, and it creates a particle. in a state, in some arbitrary state. So when a creation operator labeled by state 3 acts on the ground state, it creates a particle in state 3. But when it when an annihilation operator labeled by state 3 acts on the ground state, you can't annihilate a particle in state 3 because it's empty. So it gives you 0. So those are kind of the rules. And these are called anti-commutation relations. So they're like commutation relations for that you may have seen in introductory quantum mechanics, but instead of a minus, you have a plus here. So for fermions obey anti-commutation relation. So this is this you always see as the non-interacting Hamiltonian. Is the energy of the ith state times the creation and annihilation operator, also labeled by the ith state, and the sum is over all states and spins. So how is this Hamiltonian? All right. So one thing you can do is just go over like what it does. Go over the sum and see how it acts on the system. So this Hamiltonian acting labeled by state 1 acting on this will annihilate a particle in state 1, and this will create a particle in state 1. We'll put it back in. Then it'll just give you the energy times the ground state. So see for label 1 already gives you the energy times the ground state. So this acting on the ground state gives you energy times the ground state. So you go through all of them for so you go to the next spin, you also get energy ground state. For label 2 you get 2 times E2, and for label 3 you get nothing. Because of the anti-commutation relations, you get E3 ground state minus E3 ground state. So you get 0. Alright? So when you put it all together, you get the Hamiltonian acting on the ground state returns the sum of the energies. So this is, in fact, a free Hamiltonian. When it acts on the ground state, it returns you the sum of all the particles in your system. The sum of the energies of all the particles in the system. So that's a free Hamiltonian in terms of creation and annihilation operators. The interactions, the perturbation to the Hamiltonian are now interactions. And for example, the Coulomb interaction looks like this. It is this looks like a Coulomb or a Hart return. It depends on whether you switch the indices here or not. And then you have creation and annihilation operators. So this is a little bit more complicated to visualize how this acts on the system, so we're not going to go through it. But you can already see how this is some kind of charge density integrated over with the Coulomb interaction, right? So this has some a familiar form in terms of classical electrostatics, or yeah.
Are you going to denote, label this matrix element as like V with many indices for later?
Yes. Sorry. This should be here. So this matrix element later I will call just V I J K L or some other arbitrary letters for label, just to label the annihilation creation operator indices. Okay, so in a many-body perturbation theory, one uses the Heisenberg representation of a time-dependent operator. So we have a time-dependent creation operator, where you have e to the I, and here you have the free Hamiltonian. But the eigenstate of the free Hamiltonian is the energy. All right. So also one expresses the ground state in terms of creation and annihilation operators. So you run your DFT, you get a picture like this: 2 particles in state 1, 2 particles in state 2. Then you have what we call a Fermi level, and then you have your HOMO. This is the HOMO, this is the LUMO, right? And you have 0 particles and 0 particles. And you can label this ground state in terms of creation and annihilation operators acting on some vacuum state. Okay, so we also so important point here is time-dependent creation annihilation operators and ground state in terms of creation annihilation operators acting on the vacuum state, which is just zeros in for all your states. Okay, so what is the propagator? So this is kind of where the connection between time-dependent perturbation theory and many-body perturbation theory is. So in class we calculate expansion coefficient for the time-dependent wave function. In many-body perturbation theory, one calculates what's called the propagator. Propagator is also known as the Green's function, which is a solution to a time-dependent Schrödinger equation, which is where the word G comes from in GW. G is the propagator. Is when you take your Hamiltonian in as kind of like expectation value of your Hamiltonian in the ground state, where this Hamiltonian is made up of these time-dependent creation and annihilation operators in the Heisenberg equation. So substituting it in, you get some delta functions, you get a theta function, right? So you all know what theta function is. So it's 0 up to the Fermi level, and it's 1 above the Fermi level. Well, no, in this case it's 1 below the Fermi level and it's 0 above the Fermi level. So this is what gives you Green's function for holes and Green's function for particles. So Green's function can tell you how a hole propagates through your system. And one can Fourier transform this by standard Fourier transformation, and in the Fourier representation of the single of the free particle looks cleaner. It's this expression, but when you see when one integrates over all omegas, for the whole propagator you get just the energies of your particles up to the valence band, up to the Fermi level, and if you integrate the particle propagator, you get the energies of your unoccupied orbitals. So if you run just DFT and you calculate your free propagator, you'll just get the energies of your Kohn-Sham orbitals, right? So that's promising that we have a theory that works, right? Because the free Kohn-Sham orbitals that don't interact with each other should give you just their energies. So now one takes, one introduces interactions, and interactions are introduced in this expectation value of the ground state for the free propagator times the interaction to whatever order in perturbation theory you want to go to. And there is a sum over all orders. So that's important. So these just time ordering is another technical detail why you have to time order it. So the GW correction introduces the Coulomb interaction as a perturbation. So the GW correction tells you how a particle propagates through the system by interacting with the Coulomb interaction with other particles around it. Yeah.
Can you scroll back? And can you quickly explain, illustrate where this expansion comes from? Is it exact? Is it approximation? Is it derived from somewhere?
It is exact.
Make connection to what we did in class.
It is exact. It is exact, but it's an infinite series. You have to come up with some kind of resummation. So you need an expression.
How does one derive this?
It starts with you need the Gell-Mann-Low theorem, and then you need Wick's theorem. There's
general idea. Would you get if you just consider perturbation of next and next order and then add them together?
Yes. So this yeah. So in class, what we did is we got some, for example, second order coefficient as a function of time was something like 1 minus 1 over h bar squared, 0 to t, and then we had some Hamiltonian, psi a, psi b, time-dependent Hamiltonian, but we need another index for time, right? We integrating over t. So it's b, right? dt, integral. So to the next order, 0 to t prime, psi, I think it was now psi b, psi a, h of t double prime, because you need another time index a, dt prime, and so, well, this is just second order. But if you want to include all orders, then you can come up with an expression that gives you, it won't be a summation, it'll be, yeah, well actually it'll be the Hamiltonian to some power, right? You kind of see how this is the Hamiltonian to second power here, because you got Hamiltonian and Hamiltonian. But there is technical details in this indexing and how you integrate over time. So here, if you can see, if you take this to second order, you get the interaction Hamiltonian times interaction Hamiltonian times the creation annihilation operators that refer to that we got from the free particle. So, okay, so what I wanted you to get up to now is you have creation and annihilation operators, they create free particles, and you have perturbation to your free Hamiltonian that introduces interactions. And you have a theory that allows you to go to an arbitrary order, and any order, any order that you take, any next order that you take in the perturbation theory will give you corrections to your free particle propagating through the system. So this is the free particle with no interactions. So if you run density functional theory, you've already kind of calculated this. But now if you take the Coulomb interaction to first order, you have just one of those V, P, Q, R, S that we introduced earlier, which was an integral over 4 Kohn-Sham orbitals in the Coulomb interaction, 4 creation annihilation operators. So to get an expression for this, one can use the help of Feynman diagrams. That's what Feynman diagrams kind of help you keep track of the terms that you get in your perturbation theory. So, for example, you get a term that looks like this: free propagator, and then you get a free propagator with different energy, Coulomb interaction, and a free propagator. So this is kind of like a particle moving through the system, interacting with another particle, changing its energy, and exiting the system with its initial energy. Right? Maybe not exactly correct, but this is how you can interpret it. So this is the first order correction to the particle's energy due to the Coulomb interaction. So this is one diagram that you can get. But to second order, you gotta, okay, so to second order, there are two different diagrams that contribute to the particles, to the correction to the particle's energy. So this is where Feynman diagrams are helpful. So any way you can draw a Feynman diagram, if you can find a way to draw a different Feynman diagram, that's a correction to your propagator, right? So this is how you can think of it. This is a free propagator, and whatever happens in the middle is a correction to that propagator. So if you have 2 Coulomb interactions in the middle, that's correction. And here again, now we have a free particle and free particle with the same energy. In the middle, we have 2 Coulomb interactions and kind of like 3 particles. So it's kind of like a particle going through the system, interacting with the Coulomb interaction with another electron hole pair and exiting the system. So what you have to do is you gotta take all orders of perturbation theory into account, because they all give you some contributions. So to some arbitrarily large number, arbitrarily large order in the Coulomb interaction, you get some crazy diagram that looks like this. That will be impossible for you to calculate. Another thing you have to do technically is you have to what's called dress all the vertices. So you have to account for all the interactions when the free particle when the free particles interact with the Coulomb interaction. You have to account for everything that can happen in what's called the vertex. And to arbitrarily large order, you can get some crazy stuff that looks like this. You never calculate this. But there is a way to resum some of the diagrams. So if you only take diagrams that look like this, where you have a Coulomb interaction and then what's called an electron hole bubble, and then 2 electron hole bubbles, and then you can add a third one like this, only this way. If you only keep these diagrams, then there's a mathematical expression that relates the expression for this Coulomb interaction. From this diagram, you get an expression that looks like this: Coulomb interaction, electron hole bubble, Coulomb interaction, and so forth. And this is geometric series. It's called what's called geometric series, which you can resum. And this is the GW-approximation. If you only keep these diagrams and throw away all other ones, and do not dress the vertices, this is what's called the GW, because this is called the RPA screened Coulomb interaction. If you only keeping these diagrams and throwing away diagrams, for example, where you have a Coulomb interaction going this way, because this cannot be resummed. This is the RPA screened Coulomb interaction, and you have a propagator in the middle that is the energy of which is changed due to this RPA screened Coulomb interaction. That's a G, and that's it for this W. And this is an expression from in every paper about GW, you see something that starts like this. So this you can transform as an operator. Whatever happens in the middle of your free propagator, not in the middle, but all right, in between your 2 free propagators, that's what's referred to as self-energy. And this can become an operator that is a function of your quasi-particle energies. So it's GW is set to correct for quasi-particle energies. So for example, an electron moving through your system kind of attracts positive charges around it, and this whole blob kind of moves as a quasi-particle now through your system. But for technical reasons, you have to, well, they're not technical. You have to subtract the exchange correlation. You have to calculate the energy due to your exchange correlation functional and subtract that, because you've already used it to calculate your free particle interaction. So if you don't discard this, you double count your exchange correlation interaction. That's why this is it. That's why this piece is. That's why you see this piece subtracted from your corrections to your Kohn-Sham. This would be like your Kohn-Sham orbitals or energies of your particles after you run your DFT. This will be the corrections, and this you have to discard or you double count.
Conclusions?
Conclusions. GW is very expensive, but it gives very good corrections to the band gap, because these because it turns out that these diagrams that we saw that is possible to resum are the most contributing in taking into account the screened Coulomb interaction. So they contribute to screening way more than the diagrams than all the diagrams that we discard in the GW approximation, which is a fortunate effect.
Okay, let's thank DEYAN. Anyone wants him to speak for another half an hour? Any questions? I have one.
Yeah.
Can you already told it, but can you quickly summarize how do you get the band gap? Before you apply GW, you just have the gaps of your unscreened particles. Just tell by words where the gap comes from.
Oh, what happened? Oh. Like this. This is the energies of your particles before you calculate this. So these are your Kohn-Sham orbitals that you can take as your Kohn-Sham orbitals. These are your free Kohn-Sham orbitals from DFT. You calculate this operate. This is a technically functional of your Kohn-Sham.
And then you
orbitals.
subtract. You find one quasi-particle, another quasi-particle, and subtract. Or no?
Yeah.
Good.
Yeah, it's right. There is a summation over n, k, and lambda here. So for each E sub n, k, you can find correction to that. And once you run it for all your systems, then you look at your new homolumo gap.
Very good. Let's thank DEYAN once again. And the next presentation is by Aaron FORDE, and it will be another deposit of knowledge towards our next theoretical considerations in class. So he will be a little less humble in the orders of the perturbation theory. He will go all the way up to second order, but he will consider a different object, not the wave function, not the self-energy, but as you see from the title, density matrix. Okay, floor is yours. You can watch yourself while speaking.
So, like the introduction said, I'm going to apply the time-dependent perturbations that we've been going over the last couple of weeks to solve the density matrix. So first of all, why the density matrix? Why do we care about it? So density matrix is a formalism where you can describe the time evolution of pure states and mixed states in the quantum system. And it's powerful for describing processes that are in equilibrium and non-equilibrium. So you can apply it to many different types of systems. So I guess the first step, what is the density matrix? So down here in the bottom left corner, so we take our ket vector, we multiply it by the bra vector, and that gives us a matrix. Because normally you do, did I say that backwards? So ket to bra. So normally if you do a bra to a ket, you get a scalar or a number. But in this case, if you do a ket to bra, you get a matrix. And we're going to call that our density matrix. And then for the Schrodinger equation, we have we have an equation for how it evolves in time, which is our time-dependent Schrodinger equation. And for the density matrix, there is an equivalent equation called the Louisville equation that describes how it evolves in time. And they're basically equivalent because you can get the Louisville equation from the time-dependent Schrodinger equation, which is shown in the left. So you do the density matrix and just time evolution. Take the time differential of it, you do apply product rule, and that gives you the commuter relationship. So we can get the Louisville equation from the time-dependent Schrodinger equation. And then just some details on how to simplify our problems going into the future. So and we kind of talked about this in lab yesterday too a little bit. So there's a couple of different ways on how you can picture the time dependence between operators and your quantum states. So in the Schrodinger picture, all the time dependence is in the state, and then the observables or Hamiltonian has no time dependence. So for our wave function, it has all the time dependence, and this exponential carries a lot of oscillation with it, so it changes quite a bit in time. So one way to remove that time dependence from our wave function is to just pull this exponential out in front, and we're going to call just our expansion coefficient and our basis state our interaction wave function. And then the nice part about that is when we describe the time evolution of the interaction wave function, it only depends on the external perturbation, not the H0. And then this is just a nice visual representation. So here, exponential, it changes a lot. So if our solution you can see it oscillates in time. But for the interaction picture, like the curve is a lot more smoother in time. So that's basically the difference between the two pictures, how it changes the time evolution of the state. So in the interaction picture, to get our density in the interaction picture, we have a general conversion. So if we start with a Schrodinger state, we just kind of sandwich it in between our two time evolution operators, and that'll give us anything for the interaction state. So this could be an operator, could be a wave function, density. To go from Schrodinger picture to interaction picture, we just sandwich it between time evolution operators. And if you take the time derivative of the density operator, we can get the Liouville equation in the interaction picture. Where the Hamiltonian, or the H now disappears from our Hamiltonian, and it just depends on our external perturbation. And then if we just integrate this, we can solve for the density matrix with formal integration, where we get an initial condition at time naught, or usually at time 0. Then we just integrate our commutation relationship. So now that we know like a form for our density matrix, we can apply a power series expansion like we do for time-dependent perturbation theory. So we expand the density matrix in a power series with different orders of corrections. And for the Hamiltonian, we can just remove H0 because we're in the interaction picture. And it just kind of cancels out once we go through all the steps. It just leaves us with our perturbation potential. And then, so there's a general form for when you look for higher order corrections for the density matrix. So for some nth correction, it's going to depend on the initial condition of the nth condition minus the integral of the commuter, where the density in the commuter is the n-1 state. So if we look for the 0th order correction, like you can't have a -1 correction, so we just say it's our initial condition. So then in the first order correction, it's going to be our first order correction at the initial state minus integrating over the commutative of the potential and the 0th order density. And we just apply that to the second order as well. As you can see, there's kind of a recursive relationship. So the density one here, like we already know the form of it, so we can stick our first order correction density into the second order, which gives us this nasty looking expression here. And that's just sticking the first order into here, which I highlighted in green. So then, for going only up to second order, we know the 3 terms that we need to add together, so we just add them all together, and I highlighted each of the corrections. So this is like a general solution for expanding the density matrix to time perturbation. And I guess I should say that we don't explicitly know like the form of these density matrix in the commuters, so we can apply a certain approximation from time dependence. So if we know that our perturbation is very small, that if we look at very short time periods, that our density shouldn't change very much. So if short time steps, like the density shouldn't change as much. So we can assume that it's in the initial condition. So for all the densities in the commuters, we can replace them with, assume that they're initial conditions. And then there are also some other simplified cases when you actually apply these to certain situations. So besides the ground state, or the first order correction to the density, or the 0th order correction to the density, like those are generally going to be 0. So for the first order correction will be 0, second order will be 0, so we can just remove those. And then usually if you average out the first order correction to integrating over the commuter, that usually vanishes. So we can remove a bunch of these to only have two terms left over basically. Our initial condition for the 0th order correction, and then our 2nd order correction for the density matrix. And then we can simplify that. We can pull a constant here, so we can pull that out to the front. And then we're left with the double integral over, where we integrate over the commuter, and then once we solve that, we integrate over the commuter of the potential with this result here. And this is just another simplified version down. So this is like the most simplified case for when you apply this in practice. So I guess main conclusions to take away from this is Liouville equation and Schrodinger equation are equivalent ways to express time evolution of quantum states. And then we can use the interaction picture to give a more stable solution. So we did the density matrix and the Schrodinger matrix, like we couldn't apply that assumption where the density changes very slowly with time because you see it oscillates a lot. So with the interaction picture, we can be more certain about our small timescale approximation. And then we can get the density matrix from integrating the Liouville equation. And then the density matrix can be expanded in perturbation theory, power series, and solved in terms of initial time steps.
Okay, let's thank Aaron. Any questions you wanted to ask him about this material? I do have a silly one. What is the connection to the class material? In class, we did first order in first order time-dependent perturbation theory for wave function.
Mm-hmm. So, I guess so first order correction corresponds to the wave function to the first power. So here we see that this is the 2nd order correction after we did all the simplifications. So like the double integral. So the 2nd order correction corresponds to like a first order density matrix. Or not first order density matrix, but.
So you want to say that first order correction to wave function corresponds to 2nd order correction to density matrix?
Yes.
What is this commutator? The commutator, the potential and the density. So you have to compute. So you have to come up with an expression for that yourself beforehand. What is the computational relation between the density and the potential? Time-dependent potential and density commutator.
I guess it would depend on. I guess normally, like generally we don't usually know what this density is, but we can assume it's an initial condition. So if we know the initial condition, then you'd be able to figure out the commutation or the commuter relation between them, because you would know your external potential as well, ideally.
So what you're telling you're not showing the prescription for practical calculations.
Right. This is just the general form.
More questions to Aaron? 1, 2, 3. Let's thank Aaron once again. And we do have 3 presentations in a row that focus on applications. So the presenter number 3, Brendan Gifford, will try to draw connections between time-dependent perturbation theory and nuclear magnetic resonance experiment.
All right. I apologize in advance because the last 2 presentations have been, how would you say it, somewhat rigorous, whereas my presentation will probably be slightly more hand-wavy. So.
I welcome that.
Okay. So today I'll talk about NMR then as a time-dependent, or as a solution to time-dependent perturbation theory. So we're all familiar with NMR spectroscopy, right? We've all spent a lot of time in an organic lab. It's probably not true, but in NMR spectroscopy, what we're essentially doing is the broad concept is you'll be shooting a sample in a strong magnetic field with radiation and determining at what energies the spins flip in order to get some information as to the chemical environment of the nuclei, right? Because if we can get some information to the chemical environment of the nuclei, we can then determine the connectivity and how the molecules are put together. So So in this, so nuclear magnetic resonance spectroscopy, it relies on two spin states and the relative populations between them. And so if we were to imagine nuclei with spin, if we didn't have it in an electric field, they would all be randomly oriented, right? The spins would be completely randomly oriented.
Magnetic field.
Yeah, in the absence of magnetic field, they're completely randomly oriented. But once you turn the field on, or put them in a magnetic field, now the spins are all going to align themselves with or against the magnetic field, specifically depending on the energy, which we'll talk about in a bit. So if we imagine putting these spins into a large in a large spectrometer with a strong magnetic field, each electron moving about the nucleus generates its own magnetic field. And these these magnetic fields from the electrons are going to oppose the external magnetic field and make it so that the magnetic field that's seen by the nucleus is either slightly smaller or slightly larger. Actually, if it's with the magnetic field, then the external magnetic field that the nucleus sees in the absence of the electrons. Right? So it looks something like this. We're aligning all the magnetic fields with the external field or against it, depending on the energy, and then we'll be considering adding or subtracting that little electronic field. But that's not what we're going to talk about today. So there are two spin states, as we discussed. In the absence of a field, they're degenerate. So that's where we have completely misaligned or randomly aligned nuclei. But then when we turn on the field, we get two non-degenerate energies, or states with two non-degenerate energies, and they're given by this equation here. So if we look at this equation, we have B sub 0, which is the external magnetic field, and then some constants. So this constant, which is, what is that symbol? Anyone know? It might be too small to see. Gamma. Okay, so gamma. So it must be lowercase gamma, right? Okay, so the gamma here is related to spin in that it describes the tendency for the nuclei in the external magnetic field to not just spin on their axis like this, right, Jabed, like this, but instead like this, right? So they're actually, instead of just spinning, they're spinning off center, and so they're going to precess, right? So we can imagine these nuclei then as tops, and so we would have some nuclear precession, and so the nuclear precession has an angular frequency, which is involving the strength of the external magnetic field, and then this constant, I think it's gyromagnetic constant. And so really when we're visualizing these nuclei in this external magnetic field, we can't think of them as just spinning on axis, but really have to think about them as wobbling. Okay, so I'll refer to this as wobble. And so we'll come back to that in just a moment. So if we wanted to make this, the nuclei flip, or if we wanted to see the spin flip, where it goes from the vector of the magnetic field generated by the nuclei up to down against the applied magnetic field, we would have to add energy. And so in order to do so, what we're going to do is we're going to add energy with a perpendicular electromagnetic field. Okay, and so we'll look at it kind of like this, where we have our Hamiltonian of the external magnetic field. Just has some energy, which we'll go ahead and put in terms of the external magnetic field in the next slide. And then we're going to be adding the small perturbation, which is the energy of this external magnetic field.
So you do have two external magnetic fields.
I'm sorry, not magnetic. I lied. The second one is electromagnetic.
But one is static, another is changing.
Changing, correct. Yes. Yep. So yeah, the external one is just a static magnetic field, and then you have the electromagnetic field, which you're generating inside or in the system, and you're generating it perpendicular to the static external magnetic field. All right, so if we if we kind of add these up, we can think of adding, say, this external magnetic field is going to give the static external magnetic field, I should say, gives us these on-diagonal elements, and so then the external field which we're applying we'll consider as a perturbation, which will give us these off-diagonal elements. And so if we want, remember we had the equation which describes the frequency of the wobble. So now instead of just describing the external magnetic field instead of describing this internal magnetic field as a strength, we're going to take some of these prefactors and then we're going to include them with the internal magnetic field to now instead just describe it as the wobble, which would be seen by in the system, I should say, the wobble of the nuclei. And then on the off-diagonal elements, we'll consider this the frequency of the electromagnetic field which you're using to make the system resonate. All right, and so this is our overall equation that we have to solve, and we went through it all in class.
Pardon?
And yeah,
Can I interrupt and ask in the
yeah,
middle?
go.
So you do have three constants: omega sub 0, omega sub 1, and omega without subscripts.
Oh
Can,
yes.
Can you briefly summarize difference of these three?
Okay, so the omega 0 then is going to be the frequency of the actual
Okay.
wobbling, and so that is describing the energy difference between them. And so then the omega, or just the omega, without the subscripts, is the frequency of the incoming electromagnetic field. And then this omega 1 is
Intensity of spin flips.
the intensity of spin flips.
It is frequency, how quickly it
Oh.
will flip up and down, and omega 1 is much smaller than omega naught.
Right. Yes.
Okay.
Okay. And so then when we solve it, we can say how this population, so B and A are the population of these relative states, right? So of the ground state and the excited state. And so we want to say how the population of the excited state, or how frequently it gets populated, we would get an expression that looks like this. Right? And so if we were to analyze that expression carefully, the first term is just rapid oscillation, and so we'll say it goes to 0. But then the second term approaches 1 when omega equals about omega, or twice this omega, right? Omega naught. And so what we can say then about the system is we would expect to see the population of state B growing the fastest when omega and omega naught are on the same order of magnitude, or actually probably about equivalent. So in other words, we would expect to see the excitation happen the fastest, or to the highest degree, when this wobble of the system matches the incoming frequency. And so then we can use that to our advantage because if we're scanning the internal frequency, then we can know something about the wobble and the internal magnetic field which created the wobble in the first place, according to the original equation that I had. Actually, I don't know if I showed that one, but so this wobble frequency, the wobble frequency is dependent on the external magnetic field and the constant. Kind of make sense? Okay, so this gives us a way then of quantifying the magnetic field just by monitoring the external frequency, and then we can know something about the environment of the electron, or of the nuclei, in terms of how much shielding it sees from external, or shielding from the external magnetic field it sees from electrons in the environment, which are creating their own nuclei, or their own little magnetic fields. Make sense?
Done?
Done.
Perfect. And any questions or comments or corrections?
Were you calculating the rate of transition from what to what?
So I'm calculating the rate at which the transition from this state to this state occur. So we would generally expect in a sample that most of the population would be in the lower state, right? There's almost no population in the excited state, or I'm sorry, in the higher energy state. And then, we want to know the rate or the tendency of them to go from this to this. And so what I'm determining is the point at which that happens fastest, to try to correlate that excitation process to something physical in the system, just to give us something cool to think about in terms of why these things are actually exciting. And once you reach a point where this state is as populated as this state, then you don't get any more signal. And they call it saturation. And then but that you don't really see very much.
Right?
How do you incorporate the chemical environment into this calculation?
So the chemical environment is just giving a small magnetic field into the large magnetic field, right? So essentially this magnetic field, which is seen by these nuclei, are going to change dependent on whether or not electrons are present. So it's already incorporated then in this large B sub z in the external magnetic field, because this external, okay, so let's call this, it's the external magnetic field, which is the magnetic field seen by the giant magnetic field in the spectrometer plus or minus that seen by the electrons, or that provided by the electrons. So this B sub z is going to be slightly bigger or smaller if the electrons are shielding or contributing to the magnetic field.
More questions? Can you please go to the last slide? No, yeah. Any typos, any corrections needed to be applied here? This bracket?
Oh, yes. Yeah, the T should be outside that bracket. That's true. I'm
So
sorry.
you can make correction in your notes.
Yes.
Okay, let's thank Brendan for entertaining us with practical application of nuclear magnetic resonance spectroscopy. And next, two presentations will deal with so-called CW optical spectroscopy.
Thank you.
Although we understand that there is a time dependence because electric field is oscillating, it is slowly changing occupations, and there will be no quick time changes, although everything is derived through time-dependent perturbation theory. And the speaker number 4 in the overall line, MOHAMMED ABU JABED, will tell us about the phenomenon of the spontaneous radiative emission from the excited state of atomic or molecular system. For yours?
Thank you. So, as I said, first I want to let's see what's happening if some atoms come under the radiations. So, it's three incidents can be happen. The first one is atoms can emit photons, and then it's known as a spontaneous photon emissions without absorbing any light. And then another one is if they can absorb the radiation as a photon, and then it is known as absorptions. And after the absorptions is another process. But then another one is saying that after the atom can absorb the photons and then can emit the photons maybe in a higher energy. So this is known as a stimulated emissions. So first I will look on the perturbation theory. I want to just calculate what's the probability to get an electron to excited to the higher energy by absorbing electromagnetic radiations. So since the electromagnetic radiation, we can write the electromagnetic radiation by these equations, and this is only considering the monochromatic light, that's according in the z directions. So this will be the part of Hamiltonians, first order, this one Q and E naught Z cos omega t. And then this is the Hamiltonian for getting the electron from the B, this excited state, to the A. And this is a fancy letter. The P is giving us this is the dipole, transition dipole moments from there. Is giving us a transition dipole moment in the Z directions and from the B to A1. And so we know this term from our class, and then so probability of the transition from A to B should be by through this formula. So now I want to move on the spontaneous emission. Sometimes spontaneous emission very seeming to unusual, but we can compare a system from with a harmonic oscillator, because if we by harmonic oscillator, all particles are always in the high energy, even in the 0 degree Kelvin. So by observing the what is it called, background radiation. By observing the background radiation, electron can be in the excited state in any time. So it can emit the energy and going down to the ground state. So first, if I want to take a look on the excited state lifetime of this one, we can compare this one by calculating this one. First one is giving us.
Can I interrupt and ask in the middle?
Sure.
So above your energy diagram for harmonic oscillator, you have some tower, like greenish semisphere and reddish. What is it?
This one is giving us up to the z directions by this is indicating the unbound state, or maybe from the.
But can you explain what is green part of this image and what is red part of the image? What is
green part is a 2-state, and red part is just introduction of these two images.
Were you planning to show like mirrors and the mode of a laser mode in the resolution?
I was actually want to put this information, but it's coming up with this image. I don't understand. This image is clearly one I took. Yeah. But this one is giving us.
Yes, exactly. Two concave mirrors and light going between them with a frequency omega. And then the amplitude of this light will behave like harmonic oscillator. Okay? Please keep going.
So this one is a transition dipole by forming here, and if we consider the
what? Not transition dipole.
Sorry,
oscillator.
Oscillator. This one oscillator strength, and this one is defined the population at when the time is 0, and then we can get a population of the excited state at any time t by from this formula.
But can you point oscillator strengths on the first equation? Letter F.
On this one? This one is oscillator.
And W, what is W?
W is saying the transition dipole, I guess.
Probability? No.
No, probability of going the excited state one. Yeah. And then, so this is the lifetime. So lifetime should be, inverse lifetime will be equal to probability of transition from this one excited to the other state. And so this one is an example of the lifetime of any state in the hydrogen atoms. So if we want to look on this, and the 4s is showing that highest excited state, because the probability of the excited mode that time is the highest. And
what do you mean highest? Longest?
So longest, yeah. Sorry, my best term. And then the lifetime of the 3s is longer than is a 2p is showing in the 2p. And now if we emit the light, we want to take a look on what would be the shape of the emission light. So because in our calculation we saw that it should give a sharp line, but actually the lifetime is non-zero lifetime, so that means there have some uncertainty principle according to the Heisenberg energy uncertainty principle. We can say that there should have h over t uncertainty. These are typos. This c is nothing. So since they have uncertainty of h over t, the line width should be that emission curve should have this y h over t plus t or h over tb. So this one is h over ta and h over tb plus this tf. So now I want to calculate this line width. How we'll get it? That's on before the time started. We considered that all higher energy state is populated. That's why CB equals T. These are linear combination coefficients. And with the time, this CB is changing over U by 2 tau. And then we can get a wave functions at the time with the time evolutions by using this formula, and it's also changing the with the phase accumulation term with the EB minus IH over 2 TB. But before the time started, this is the initial wave functions before when time t equal to 0. And then if we want to compare these two wave function when the time start the propagations, is showing that the initial wave functions energy and the propagate energy wouldn't be same, is giving us a different energy, and this energy including one complex term. So the propagate wave function wouldn't give us a constant energy, it would give us a uncertain energy in this one. So by using this all of math, we want to figure out the CB, or the probability of the ground state for term. So it's only this Einstein coefficient. If you look on this big formula, this only depends on this term. So now we want to compare the t and with the lifetime of the excited state. If that lifetime is t is longer than excited state lifetime, it will give us this equation. We can simplify with this one. So it depends on t, and we can get a maximum value when t equal maximum, and we got a v over EB minus EA. This is a maximum value, and half-life of the this one when the t equal to t half, then we will get this from this tau v over tt is tau v is not, sorry, gamma v is not as a half-life of this one. And if we plot, we will get the maximum emission here, and this is a line width, and this is a half-time of this kind of things.
Okay, let's thank Jabed. Any questions to him? I do have a couple. Can you go to slide number 4? Yes. Yes. Okay. Which equation here reminds you at most Fermi's golden rule?
This one is reminding us.
Good. Correct.
Because
Now explain it to Levi.
Wait, I didn't see which one you pointed to. Which one?
Which one? Show it once again.
this one, because it's
No,
energy-
you are showing
No.
different. Show once again what you were showing first.
This population, this final one.
Yes, correct. Now explain.
So Fermi golden rule, we comparing this. Energy state is continuous in energy, so we can add as a sum of this all excited states should be.
Adding together several channels of the reaction.
And you'll get a lifetime.
Typically it is integration, but here it is summation. Good. What else is present in the Fermi's golden rule? Density of states, which will come up from the summation,
And energy of the
interaction matrix element squared. Where is the interaction matrix element squared?
It's coming from a-
No. Navigate by your fingers through the first equation. Further. Yes. So what is F?
Isn't it oscillator strength? Well, I mean, yeah.
Oscillator strength. How does it relate to transition
Dipole moment.
matrix element?
It just two, and then
It
we get
is-
transition dipole moment. Yeah.
Transition field times transition dipole moment in which power? First or second?
Second.
Yes, correct. So interaction matrix element is field times dipole. and we take it square. And here it comes through the oscillator strengths. So the first and last equations together on the slide are implementation of Fermi's golden rule in application to spontaneous emission. Good. More questions to Jabed? If not, let's thank him once again. And the next presenter, Samuel Brown, will summarize and give more details on the optical spectroscopy in CW regime, where fields are, intensity of light is more or less constant. And floor is yours.
All right. So I'm just going to go through the derivation of Einstein's coefficients. So there's three different coefficients that he has. A21, so that's just spontaneous emission, where you have electron going down into the lower energy state. Then stimulated emissions, a similar one, but you have another photon in there to help. Then absorption, which is what we'd expect electron being excited into a higher energy state. Then in equilibrium, I'll come back to this, we'd expect, so the number is the number of molecules in the system that have that same state. We'd expect this equation to hold true. So number of electrons that are excited to be the same as the number of electrons that are emitted or lowered in state. So going through this, we have our wave function, and then we have this as a time-dependent wave function. We have these different coefficients, and then the wave function with the time-dependent operators, and then we'll use this as our perturbation. So if we plug those into the time-dependent Schrodinger equation, we have a whole bunch of math, which I went through, and I won't talk about now, but we get to these equations at the end, which are our time-dependent, those coefficients that I had at the beginning. Which I'm pretty sure we did something very similar in class. We assign a periodic perturbation, instead of, because though the last one was somewhat general, we could get the equations that we had some in class as well. And this is the probability of going from state A to B. Similarly, we could get these probability for going from B to A. Then if we look at the entire spectral window, we have this integration in there, which what we talked about last time. So that just goes to pi, giving us probability of going from excited state B to A. So if we take the derivative of this, we'll get the rate, which is this equation here, which, as we saw in class, is independent of time. This was done for light coming in one direction. If we look at light coming in all different directions, we can get this equation here. Then I said we'd look at this in equilibrium again, and that's what we're going to do. So we have these different things in equilibrium. And if we use that equation, and we go back and use our equations that we found earlier, we can solve. Okay, so solving for our equilibrium equation, we get this. And if we note that Nm, you can find the energy at that state. Here we have this, which we can then compare to this equation, which is black body radiation. And then getting that, we can solve for these two different equations, which gives us our Einstein coefficients by comparison between A21 and B21. And then we also have B12 and B21.
What is G2 and G1?
Those are the degeneracy.
Good, thanks.
Which we can then get Einstein's coefficients because we had probability from earlier, and we can solve for one of them. Which, I believe that's it. There's time for
Okay,
questions.
let's thank Sam for being very short and communicating very complicated subject in a very short time. So DEYAN had a question.
So the rates for spontaneous, no, sorry, the rates for spontaneous emission and absorption should be the same.
So, yeah.
So two of the Einstein's coefficients I remember are the same from back when I studied.
Yeah, B12 and B21.
So stimulated emission and absorption are the same. Okay.
Yep. Depend what, just the degeneracy factor, but otherwise they're the same.
More questions? Okay, you designed your questions, I will ask mine. Your equation for equilibrium, where it comes from? It looks like not the starting point, it is derived from somewhere else.
It's just saying that these three things will be the same. So this equation here, B12, will be the same as these two. So that's all it is.
So the rate of absorption is equal to the rate of spontaneous and induced emission.
Yep.
But what do you mean in equilibrium?
Thermal equilibrium.
But how will this equation change if we are away from equilibrium? This is equation for N1 and N2, which are populations of level 1 and level 2. If it is not equilibrium, if there is time dependence, should there be change in time of populations?
Yes, I would expect.
So there should be a rate equation for N1 and N2 with time derivatives.
That makes sense to me.
Okay, good. So let's just mention it here. There should be d and 1 dt and second equation for d and 2 dt.
I see. Yep.
And in the equilibrium, you set up this derivative 0, and then you get whatever you have.
Yep. I see what you're saying.
I always wondered why on your so on the second to last slide, I think, where you have the final expressions for A21 over B21 of one slide. Yeah. I was always wondering why this constant that relates A21 and B21 is not dimensionless. Because right now it looks like it has units of electron volts over volume. It's the seconds cancel, but you got meters cubed on the bottom, so you're left with electron volts over meters cubed. Anyway, it doesn't matter, it's not dimensionless. So it's rate equals some dimension, some constant with units times the rate. What I always wondered why that was.
So the question is, let me translate. Do you anticipate, do you suspect any physics behind it? Or it could be a typo, or it could be worked out by careful processing the dimensions, like expressing everything in the atomic units? Or there is a specific effects?
I can say I wouldn't be surprised if I have a typo in there.
Okay. So which rate is higher? What is more probable? Spontaneous or induced?
I guess induced would be higher rate.
Okay. And if you look at these constants, it should reflect?
It's reasonable.
Okay, let's discuss it more because it can be longer than 2 minutes answer. We can make it as a subject in the class. More challenging questions to Sam? If not, thank him once again. And we do have, I hope, very brief, but at the same time, very important. Yes, so it doesn't matter. Okay. Very brief, but very important talk by the last but not least speaker, LEVI LYSTROM, who is expanding our consideration forward in time. So, last 2 presentations were dealing with optical spectroscopy, where, according to Sam, we are looking near equilibrium, when all occupations are equilibrating. There are rates for transitions, but everything is very slow and smooth. And Levi was brave enough to choose the presentation subject to look at the relatively novel area of spectroscopy, the one for which Ahmed Zewail got the Nobel Prize, the time result spectroscopy, when changes of occupations occur very quickly and when the optical excitations are used not in the CW continuous radiation or continuous emission, but abrupt excitation by short pulses. So it is just Levi's opening the door for this interesting journey for all of us. 4 years.
Thank you. So, femtosecond spectroscopy. So, why femtosecond? The reason that we want a femtosecond is we can look at, we want to probe this first excited state, but it's not optically active, so it's very hard to gain information about the first excited state. So what we can do is we can excite to a higher level, and then we can, after a short delay, we can have a wave packet in the ground state of at the point where it's came to equilibrium in the excited state, and then what we can do then is take another photon and excite, and then see how it goes, and we can do that to probe the excited state. This can lead to like RSA, so reverse satural absorption, where we want to populate this first state because from the 2 dotted lines, the oscillator strengths are very high, so there's a high probability of absorbing light, so that can lead to nonlinear optics. So what they do in the theory and experiment is use this window time, a probe delay time, and a doorway, which the window time is this, and then you excite up, just like I showed in the last slide. The delay is when it relaxes, and then the window is when you excite, and it doesn't necessarily have to come here. I just didn't want to draw a bajillion lines. So that's kind of the big picture. And in the next slide, there's going to be several equations, and the W means window, the D means door, and then the like fancy F means this like delay time, and then here are the time notations. Oh, okay. So then we get this big equation. So what it pretty much is saying is we're going to have something happen on a window, then we're going to propagate on the excited state, then we're going to do something in the door, and this is split into the electron and the excited state and ground state. So these are the equations. Personally, I don't really know what all of these equations mean, but hey, that's what happens. So in conclusion, we can probe the exciting window, the delay time, and then the door. So with that,
okay, let's thank Levi for beating Sam in time interval spent for presenting complicated subjects. So any questions you wanted to ask Levi?
I feel like Brandon has one.
I do kind of have one, but I don't know.
And I have 2. So
it might be a terrible question.
Okay.
Okay, so why do we have to pump really fast again?
So if you don't pump, if we go kind of back to Jabed's, once the wave packet's here, there could, or Jabed's and Sam's, there could be emission. So if you get the wave packet where you want it and you don't have the timing correct, then you will not be probing the right state.
You want emission from dotted state, right?
It depends on the application. So like RSA, you don't want emission. You want it to be exciting up, so you populate your excited state, and then that leads to your non-linear optics. So it depends on what application you want. So like if you want LEDs, then you do not want this state to be long, you want it to spontaneously emit. Does that make sense?
Sure, I buy it. No, it doesn't make sense.
No?
It's not application. It is just experimental technique. You do not use it in any industrial applications.
Usually it's used to measure the tree pedestal lifetime.
Huh?
Is it used for tree pedestal lifetime to measure?
Yeah, you can.
It depends on it.
Good. You are asking, you are kind of prompting
I'm
me
contributing,
to the
yeah.
question that I was going to ask. And everyone is welcome to contribute. So, which information can be measured by this type of techniques, which was not possible to measure with steady state spectroscopy? Why this technique is needed? What is the benefit?
So as Jabed said, lifetimes. And if your emitting state is not optically active near the ground state while, then you can't really populate that. So these techniques are to kind of understand the non-easy transitions to probe, kind of. Because here it may have no optically active, however, you could have, if we look here, like this could be one adiabatic state, here could be another adiabatic state, and there's energy splitting, so this could be two different nature states if you're in the adiabatic approximation instead of the diabatic. So depending on the nature of the excited states, that would lead to different properties where here you would emit light, here you would not absorb that well.
Okay, so Levi did answer that these time resolved techniques would help in at least two cases, when we deal with dark states and when we need explicit time information on lifetimes, right? Anything else we can see? Any other benefits that can be extracted through time resolved spectroscopy? Well, expanding on dark states, which states are typically dark?
Charge transfer.
Yes, so one can monitor, direct monitoring of the charge transfer dynamics. It's not for monitoring it in the PV cells, but while designing PV cells, you can measure their properties in the lab. Okay, what else? Energy transfer?
Yeah.
Would you do show potential energy surfaces here?
Yes.
So the function of electronic energy of the interatomic distance. So can you track the events of bond breaking or formation with this technique? Or just drastic elongation?
I believe you can.
Maybe, yes. So the time resolved techniques can help to follow reaction dynamics.
But you would have to come up with an experiment that you could do simultaneously to monitor it.
So there are more challenges than answers. More questions to Levi? I have another one. So when did this class of experimental techniques was born? When it became possible to use?
I believe like 1987, 87-ish, I thought.
So, about right. Was it before or after regular CW spectroscopy?
Far after.
Why? What was wrong 200 years ago?
They can't really produce the femtosecond laser pulses.
Pulses. pulses. So the limitation to run this technique is generation of short pulses. Correct. I didn't formulate the question, but you already answered.
Okay.
So the prerequisite to run these techniques, which give healthy benefits, is to be able to generate short pulses. More questions? If no, let's thank Levi once again. And thank all speakers and presenters for very nice overview of possible applications of time-dependent perturbation theory, or overviewing the areas of research that are connected to the class material. Before, in the last couple of weeks, we were dealing with low intensity perturbations. And when we, being inspired by Levi, when we continue our class, we will look on the perturbations that have higher intensity and the changes are more drastic. Next week is the break. So we see each other in about 10 days, Tuesday after the break. Thank you much and have a pleasant break.
Oh yeah, I would have had no idea.
So
Meeting number 16 is dismissed.
what is
You don't
this
remember
technique
my
then?
animation?
Animation?
Yeah.
From what?